Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch all my videos on my channel. Weir is a geometrical opening made of concrete or masonry which is constructed across the river. So due to the construction, the level of water at the upstream side rises and the excess water that flows over this weir towards the downstream side. A weir is similar to a small dam. However, in the case of dam, the excess water that flows to the downstream side only through the small portion that is called spillway, whereas in the case of weir, the excess water flows to the downstream side over the entire length. So the figure shows a weir constructed across the river. It is freely discharging to the downstream side. So when the water approaches this weir, the surface profile is getting curved. In order to avoid the curved nature of water surface profile, the H is measured at a distance 4 to 5 times H from the upstream of this weir. So weir is classified based on the shape of the opening, shape of the crest, effective sides of issuing nap, discharge conditions. So based on the shape of this opening, weir is classified into rectangular weir, triangular weir and a trapezoidal weir. And based on the shape of the crest, weir is classified into sharp crested weir, narrow crested weir and broad crested weir. The figure shows the sharp crested weir. So in the case of sharp crested weir, the nap touches the upstream edge of the weir and flows free of downstream edge. Whereas in the case of narrow crested weir, the crest width is very less and the nap flows over the entire crest. But in the case of broad crested weir, wide crest is available. So when the flow approaches, water surface drops when it flows over this weir crest. Because of this wide crest, the flow velocity increased, which causes the drop in the head. According to the effect of sides of issuing nap, the weir is classified into weir with end contraction and weir without end contraction. If the sides cause contraction of the nap, then it is called weir with end contraction. Otherwise, it is called weir without end contraction, or it is called suppressed weir. Weir is also classified based on discharge condition as weir discharged freely and submerged weir. Since water level in these two cases are less than the crest of this weir, these two weirs are called freely discharging weirs, whereas in the case of submerged weir, downstream water level available is above the crest of this weir. So this type of weir is called submerged weir. Now let us discuss about the different type of weirs. So basically there are two types of weirs are possible. One is with sharp cornered. So in the case of sharp cornered weirs, when the flow approaches, so air pocket is trapped at the upstream corner. During the course of flow, the air is sucked by the flowing water. There is a formation of negative pressure here. It promotes cavitation. Finally, this portion of the weir is getting damaged. So in order to avoid that, this sharp corner is to be converted into round corner. Z that is equal to weir crest height and B that is width of this weir. H is the head upstream of the weir and H is the height of the water that is available over the weir crest. So weirs are classified into sharp crested weir. So in the case of sharp crested weir, the width B is less than 0.625 H. So that means jet of water touches only at the upstream edge of this weir and it flows free of this downstream edge. In the case of narrow crested weir, the width of the weir crest is higher than 0.625 H, but it is less than 2.5 H. When the water flows over it, the jet of water remains in contact with the entire crest. So the figure shows a broad crested weir. So when the width of the crest of the weir is higher than 2.5 H and it is less than 10 H, it is known as broad crested weir. So in the case of broad crested weir, when the flow approaches, it flows over the entire crest. At the same time, water surface drops when the flow takes place over the weir crest. That is due to the increasing flow velocity. Now let us discuss about the discharge computation of broad crested weir. So the figure shows a round cornered broad crested weir. By applying Bernoulli's equation at these two sections, this capital H, that is equal to H plus V square by 2G. When the flow approaches towards this weir crest, the water surface drops just because of the increasing flow velocity. So H equal to small h plus V square by 2G, or V equal to root of 2G into H minus H. Since depth of water available over the weir crest equal to H, so the flow area, that is equal to L into H, where L is the length of the weir. So discharge equation, that is Q equal to AV, which is equal to CD into L into H represents the flow area into velocity. So in order to calculate the discharge, we have to measure two H values. One is just upstream of this weir and other is over the weir crest. However, based on the experiment, it is found that in the case of broad crested weir, the flow adjusts itself to have maximum discharge for the available head H. The condition of maximum discharge for the available head H is obtained by differentiating this expression with respect to H and equating into 0. So by differentiating this expression with respect to H and equating into 0, then we can establish a relationship between this capital H and small h. So it is H equal to 2 by 3 H. So we can conclude that if the head available over the weir crest, that is equal to 2/3 of H, then the discharge is maximum, and the maximum discharge, that is equal to 1.7 CD into LH raised to 3 by 2. If we are considering the velocity of approach, then this equation turn into 1.7 CD into L into H plus HA raised to 3 by 2. Now let us discuss about the discharge computation of submerged weir. If the downstream water level is above the weir crest, then we can call that weir as submerged weir. So in the case of submerged weir, discharge capacity is more. So during the flood, the weir is in submerged condition. So during the submerged condition, the flow over the weir crest adjusts in such a way that it will increase the maximum discharge capacity so that flow is easily diverted into the downstream side. Discharge over the submerged weir may be obtained by dividing it into two parts. The first part is the freely discharged weir, that is by considering the water level at the upstream side and the downstream side. So this portion we are considering that the weir is discharging freely, and this portion we are considering as a drawn orifice. This is the first part and this is the second part. So for the drawn orifice, we consider the level difference between the crest level and the downstream water level. So Q1, that is the discharge correspond to free weir, that is we considered the portion between the upstream and downstream water level. So Q1 equal to 2/3 CD root of 2G into L into H1 minus H2 raised to 3 by 2. So this is the head of water that is available just upstream of this weir. And for the second portion, the flow area, that is equal to L into H2, and velocity depends upon the level difference between the upstream and downstream water level. So Q2 equal to CD2 into L into H2. L is the length of the weir and H2 is the depth of water available. So this becomes the flow area into velocity, and velocity depends upon the head difference between these two. So it is equal to root of 2G into H1 minus H2. So the total discharge Q, that is equal to Q1 plus Q2. If velocity of approach is considered, Q1 becomes 2 by 3 CD1 root of 2G L into H1 minus H2 plus velocity head raised to 3 by 2 minus velocity head raised to 3 by 2, and Q2 equal to CD2 into L into H2 into root of 2G into H1 minus H2 plus VA square by 2G. So in this expression 2G's get cancelled. So finally Q equal to Q1 plus Q2. Now let us discuss about the ventilation of weirs. So far we have derived the expression for suppressed weir based on the assumption that it is discharged freely to the atmosphere. So in the case of suppressed weir, the width of the channel and the width of the weir both are equal. This is called free nap. So during the free discharge, air is getting trapped between the side of the weir wall and lower portion of the nap and bottom of this channel. So the pressure here is atmosphere pressure. So during the course of motion, this air is being carried away by this flowing water. So pressure available here, it get reduced and it becomes sub-atmosphere pressure. So that time this nap that moves towards this weir wall. So since pressure here is below the atmosphere pressure, the discharge flowing is more than the computed discharge. Finally, it becomes negative pressure, it leads to cavitation, and this nap that moves toward this weir wall. So due to the close contact between this weir wall and the water, this weir wall is getting eroded, getting damaged. This is called a clinging nap. So all the expressions for the computation of discharge of suppressed weir we have derived earlier based on the concept that the weir is discharging freely to the atmosphere and the pressure here is atmosphere pressure. So in order to keep the pressure here is atmosphere pressure, we have to provide air holes, and area of the air hole that is more or less equal to 0.5% of the area correspond to length of this weir multiplied with the depth of water that is available at the downstream side. If air holes are provided, then even if the air available here is being sucked away by the flowing water, the amount of air is recouped through these ventilation holes from outside. So this is called ventilation of weirs. This will increase the efficiency of the weir. In this class, we have discussed different type of weirs and various equations for the computation of discharge. Now, the session comes to an end. For the time being, it is enough. Thank you. Your SumamMiss.